So, bless you. As you notice, I present you bits and pieces. I'm not presenting you the whole story, but you can't expect to understand a whole story in 20 hours, right? Nobody will. That will never happen. But some of you already know a lot, and in any case, it should give you an idea what's going on and which direction you further have to read. You can always ask me for literature for certain directions. Now, in general, what you of course do is you develop fundamental theory, and then once you have that done well enough, you go on and use it. And here I took a few choices. I defined the vertex algebra using locality, and then I told you one could have equally well have used duality. I told you the very same thing for modules, and now I introduced the intertwining operators using something that resembles very much the duality statement. Now, it turns out for the intertwining operators there is no good notion of locality. However, there is a third equivalent thing you can introduce. It's from a conceptual point of view the least instructive one, but it is a formal power series version of the duality. Okay, and it's called Jacobi identity. So let me state it as a remark, and we can replace locality by what is called Jacobi identity. And this is the following thing. I'll introduce this, what I call here delta tilde, in a moment. It is also a formal delta distribution, closely related to the one I introduced before, just not quite the same. Or you changed the argument, really. So here we have U and V are elements of our VOA. And it is an identity that wants to incorporate both commutativity and associativity in the duality statement in one go. So here, what you the first line relates we have the product of y in V and U in one order and in the other order. And the second line is the type of expression that appears in the last point of duality, this one that I always call the associativity type statement, where you have one vertex operator where the argument is given by the action of the other vertex operator. So this is called the Jacobi identity. I forgot the tilde again, where the tilde is the delta distribution that has this property whenever it makes sense. So if you think about it, for formal power series, that means it would be the formal power series, this formal power series. And if you compare that to the old one that we had, it's that's exactly the old one where the x is w over z or z over w. Okay, this is a remark, and it turns out for the vertex algebra itself, you can replace by locality, by Jacobi identity, or duality as you like. It turns out for a module, you can do the very same thing. You would then just have the module map instead here for this one. And you can do also the very same thing for an intertwining operators. Then you would again just replace this by an intertwining operator, and on each y you add the corresponding label for the corresponding module action. Now it turns out, so this means for a vertex algebra, you have locality, which is the best one to, in the very first place, see that you have examples of vertex algebras, because you can check the locality explicitly, and that's why one starts with that as an introduction. Now, then you show that the three notions of locality, Jacobi identity, and duality are equivalent, and the notes by E.G. Huang they explain the relation between Jacobi identity and duality. And then you try to generalize, and you observe that all three notions make sense and are equivalent on modules as well. And then you try to generalize, and you introduce intertwining operators, and you observe, at least Jacobi identity and the notion that I presented there still makes sense. And you hopefully see a striking similarity between the two expressions. It's just here we go to analytic functions, and here we still want to work in a completely algebraic framework of formal power series somehow.
Actually, the delta of Riemann, there was a 1 over z in our definition of delta of Riemann.
I forgot that. That could very well be. Yeah.
So in the thing that you've written, the first two terms, the delta you've attached to the first term, it doesn't have a z2 anywhere inside.
This one here? Yeah.
So I think he means that for the last two delta, we have Z0, Z1, and Z2, but for the first one, we only have Z1 and Z0.
It just seems a bit strange.
It seems a little bit strange. Let me check it. It might, of course, be that I miscopied, but I don't think so. But I will check.
Also, normally, are the delta tildes kind of telling you, are they playing the role of like, this is where omega over z is positive, the epsilon?
Yeah, that's what they morally say, and that means also then they morally tell you, they will then correspond to exactly where the corresponding expression converges. So now, now you have this different, and of course each notion has its purpose. And so if you want to go to physics, correlation functions, of course, this is the language you want to use. And it turns out if you want to study categorical properties, you need something like some commutativity property of tensor product and associativity property. Well, how will you do that? You will do that by some kind of analytic continuation. So you need this language to get structural properties of the vertex algebras. But this notion, but it's hard to verify on the nose that you have intertwining operators of this type. But here, this is a purely algebraic problem. So that means it's a computational problem. So maybe here you can do that. So it's as usual. Each notion has its pros and cons, and yeah. Anyway, at least you have seen the different key properties. And now let me introduce one way to get intertwining operators. I call it spectral flow. The name is due to physicists, and what I present is due to work by Hai-Sheng Li. And it's also often called not spectral flow but Li's delta operator. Yeah. So when one would like to have some kind of operator that goes from one module to another module, and at the same time and uses also a map on intertwining operators in a nice way. And this is what the spectral flow operator will do. So we take V to be a gradient restricted VOA. I just write VOA. And we are interested in a spectral flow operator or delta operator. And this will be an operator so very much like a field, which has a few properties. So if I act on a vector, I remove a bracket. So that means then it's just a polynomial in Z and Z inverse, not a. It leaves the vacuum invariant. It has a nice compatibility condition with the translation operator, with the Virasoro -1 mode. So, but you have here a minus sign that's a little bit different to before. And then the key property is this compatibility property with vertex operators, with fields. So if you take this delta operator, act on a vector V, then take the field corresponding to the image, multiply the answer from the right with the delta operator in the second variable, then this statement is that this is the same as left multiplication of this delta operator on the original field. And you want this to hold for all V. Okay, and so these are the conditions, and the statement of the lemma is if you have such an operator, then you can twist a module by this operator and you get a new module. And now I denote the module by the underlying vector space together with the set of fields or the set of vertex operators. And then we define a new module to be as a vector space, just being the old module, but the action of the vertex algebra being twisted by not the original fields, but the original fields composed with a delta operator in this sense. And the statement is that this is a module as well.
Is delta V, is it usually just y of vz for some v, or is it something completely different?
Completely different. Completely different is maybe said too much, but quite different. So it will not. And if you in particular, I very shortly introduced the Heisenberg VOA, and I told you that the complete list of simple modules are these Fock modules. A Fock module is just generated by a highest weight vector that I denoted by this ket lambda, so on which the zero mode of the Heisenberg algebra acts by multiplication of lambda. All positive modes act as zero and all negative ones freely. In particular, as a vector space, each Fock module independent of lambda is just the polynomial ring in the negative modes. In particular, all Fock modules have as underlying vector space isomorphic vector space. So this means that is an example where you see, indeed, I can have an enormous zoo of modules that have isomorphic underlying vector spaces, right? And that will also be what we want to go to. This delta operator will apply quite general, relatively general. It will apply particularly well to tell you how Fock modules are related. So we will. So that will be the main application of it. Okay. Okay.
Is it possible that in the affine case this is related in any way to twisting with like the half sum of positive roots and one doesn't understand very homomorphic or another?
Yeah. So the question is, I remember it, is how is this related in the affine case? And it is enormously interestingly related. I think not exactly as you asked, but shall I give the answer? I'll give a sketch of the answer, okay? Because it's a really good question. I'll do that in SL2 and then tell you in words how it generalizes, okay? So SL2, we discussed this yesterday, and I fixed the basis as yesterday, EHF with the commutation relation, and then for the affine Lie algebra, I just have my modes En, Hn, and Fn, where these modes run over the integers. And now I can ask myself, do I have interesting automorphisms on this Lie algebra, just on the Lie algebra? And now one could wonder, can I, for example, have an automorphism that maps En to En plus L for my favorite integer L? Right? So for example, En goes to En plus 1. It turns out indeed there exists such an automorphism if at the same time I map Fn to Fn minus L. Okay, and now let's think about the commutation relations. What's the commutator of Em and Fr? It is it's H M plus R plus the level delta M comma R. What else do I get? An M, and then the pairing of the two, and I fix the pairing of the two to be 1, if you look back at it. So now let's see, if I take now Em and Fr and compare this with Em plus L. I'm also doing this because I don't have the formulas in my head. So Fr minus L. So now whatever this commutator is, we still want it to be of this form, just instead of H, its image under spectral flow, under this automorphism will appear. Right? So let's see, we get here Hm plus L plus R minus L, so that's still Hm plus R. And then what else do we get? We get K times M plus L and I'm sorry, here I meant delta m plus r comma 0 times delta m plus l plus r minus l comma 0. So that's also the same. So and we see, if m plus r is non-zero, I don't have to do anything to h to get here. So this means I can write here delta n comma 0. But if m plus r is equal to 0, this becomes non-zero, and the coefficients here differ by L. All right, so that means in order to get an so I have to add here an L times K plus Hn. And now one can continue and verify that this indeed is an automorphism of the affine Lie algebra. It's coming from the affine Weil group, from the translation group. So it's the induced automorphism from there. And that already tells you how it generalizes. So in general, we have an affine Weil group, a translation group, labeled by coveights. That's by the coveight letters. And so that means for each coveight, so here you identify the coveight letters for the integers. And so for an affine Lie algebra, for each coveight, you have an automorphism, and it has the interesting property that it does not leave the horizontal subalgebra invariant. E naught is not mapped to E naught or F naught. It is mapped, E naught is mapped to EL. Right? And so now whenever you have an automorphism, you can take a module and you can twist it by an automorphism, right? I have a module, and now M stands just for a module of the Lie algebra, and now let's maybe call this morphism sigma L. Then I could then I define a module called sigma star of L. So this automorphism I denote by sigma L, where and what do I do is I take this module as a vector space to be isomorphic to M, right? But I require that X acting on a vector in there, the action is defined to be the action twisted by the automorphism, and usually one takes the inverse. That's just a convention. Okay, so that gives you a new module. Now, while this is isomorphic, I mean, it's just related by an automorphism, so that's what it is. But in the VOA setting, this one does not respect gradings, etc. So this means the module that you get via twisting is not isomorphic to the original module as a VOA module. Very much not. All right, and
excuse me. So I have a quick question. That is, here En or Fn or Hn, they are integers, right?
yes. Yes, they're integers. Right? And so I'm quite happy about your question, just that it's, I mean, all your questions come too early, but otherwise I like them a lot. And this is what we, so now one can ask the question, okay, we have an automorphism on the Lie algebra that it twists modules because of grading conditions. The twisting modules have no chance to be isomorphic to the original ones as VOA modules. Do I have a natural operator that irrealizes the VOA action on the twisted module? The answer is the delta operator. Okay, so that's a very good motivation for what I'm doing now. The answer is spectral flow, the delta operator. The answer is what I'm going to present. Okay, and in particular, if you now you can already do a lot for SL2, for example, because I gave you a complete list of, let's call them, interesting modules of finite SL2, of weight modules, and each such module, of course, induces to a module of the affine Lie algebra via the standard construction that we have discussed quite a few times. And now each of these induced modules you can twist by your favorite spectral flow. What happens because of this condition? These induced modules will be lower bounded. They are generated by a top level, a module of the finite dimensional Lie algebra. If you twisted it, right? So for example, remember I wrote down this E-type modules on which But now the action of E naught will, for example, be identified with the become the action of E1. So all of a sudden, E1 does not act nilpotently anymore. This means you get arbitrarily high powers of that. But that means the conformal weight of states will become lower and lower and lower. They will be completely non-lower bounded. Right? And so that means you get an enormous class of modules in a very natural way. Cool. More questions? There's a
Am I supposed to think of this delta as a line operator? Is this delta a line operator? Is that the kind of thing which it is?
line operator in what sense?
In the CFT.
And the let me think.
We can discuss it.
Let's discuss it later. So it has definitely something. Yeah, let's please discuss it later. Yeah, there's another question.
I want to say before you wipe it out, but now it's wiped out.
Yeah.
Can you say how it gives us a delta?
Yeah, that will take the next 2 lectures. Yes. I don't know. In fact, I know. I wanted to prove this statement, or at least the key thing. Shall I do that? It's somehow. Let me. Why don't I?
We are willing to. Certainly, would be nice to see a proof, but would also be nice to see an example of such.
I think it's. I think in general we decided that I more give results than technical details. So if you go back in the notes, the definition of a module, we have to check those definitions, and there's this. It's for example clear that this property ensures that the twisted operator to the identity to the vacuum is still the identity. So that's exactly why we need this one. This condition one needs so that this L-1 derivative property is still satisfied. That's also quite easy to check. And this property is the key thing. It's exactly what you need for the Jacobi identity to still work out. You could even simply have come up with this property by wondering what kind of property does an operator need to satisfy, so that if I twist in this sense, the twisted module still satisfies the Jacobi identity. It's just exactly what you need, and it's a half-page computation. Anybody who likes can take a photo of it, and then that's what comes out. Yeah, I think it's probably a good idea if we don't prove this then. And now one can. And the interesting thing is, I told you this. So the only non-trivial statement in this proof of this lemma is verifying the Jacobi identity, which follows from this property. Now, I told you that an equivalent way to define intertwining operators equivalent to this analytic version is also a Jacobi identity, which is enormously similar. And in particular, it means that a similar lemma does not only hold for twisting modules, but also for twisting intertwining operators. The proof, very nicely, is almost exactly the same. Yes?
Is there a statement like the delta operator holds in these cases, exists in these cases, or something like that?
Yeah.
I'm happy to believe that if it exists, then you can do this, the statement of the lemma, but it's harder to believe that this just happens to exist.
Yeah, so at the moment I'm just telling you, if you have such an operator, you can twist. Yeah. All right? I also gave you this erased motivation that there are these automorphisms on affine Lie algebra, and it turns out the corresponding twisted modules can be realized by the delta operator, but I have to construct that delta operator, and I want to do that. So, and the example I give is a very fairly general example, as you will see, and it's also the only known one. But it turns out this delta operator as such is also, variants of it are also very useful to construct indecomposable modules. That's a complete different story. But for that purpose, it's also really good that you see this operator. So this lemma, I can continue with the same conditions here. Then just that, and now here I take if M1, M2, and M3 are V modules, and I is an intertwining operator of that type, of type M1, M2 to M3. Then, well, what can I define? I can define an operator, I call it I tilde, which is just the intertwining operator I, but not evaluated at M1, but at delta operator applied to M1. And what is this? And the statement is this is an intertwining operator of type. You still insert a vector in M1, but it then becomes but it now acts on the twisted module, and the output is a twisted module. And that becomes now, of course, quite interesting, right? Because it means now if I have a delta operator, or even better, a family of delta operators, right? In this example, I want to suggest I have this L co-weight labels. I want to say that for every co-weight you have such a delta operator, then you also get an enormous zoo of intertwining operators by doing all these twistings. And you already get non-trivial intertwining operators by taking M1, M2, and M. Well, I'll explain that. You get an enormous amount of non-trivial intertwining operators, but let me explain this a little bit later. Okay. It turns out the quality of proving this statement and this one is equivalent. It's equally difficult. It's both a computation with the Jacobi identity. It's comparable, not hard. Now the question is, can we find non-trivial examples? And the answer is yes. This is why we do that. So what do we do is we assume now that we take a special VOA, a vertex algebra that has a Heisenberg algebra. Here, this was our Heisenberg algebra as subalgebra. So this Heisenberg algebra, we had this field. I just recall what the most important field was. Where these the modes satisfy the commutation relations of the Heisenberg Lie algebra, the affine Lie algebra of C. Just these very nice commutation relations. Okay, and now it turns out, taking these modes, we can do something. First, we define E plus minus alpha x comma z to be the following things. And here we only sum over positive integers. Then here we have either the positive or the negative modes, depending on which sign we chose here, and then divided by n, z to the negative or positive n. again, we define this because this will allow us, these two will allow us to, actually to construct the delta operator, we mainly need only the E plus. So those who already know conformal field theory or vertex algebras, they will have seen that if you look at vertex operators of lattice VOAs, they are essentially products of an E plus and an E minus. Right? That will not be a coincidence, and it will become well, but it's not important for us. Just okay.
Excuse me.
Mm-hmm.
What is alpha?
And alpha is alpha is any complex number here. And we will later see that depending on alpha we get a delta operator or not. So we will not get for all alpha, but only if it satisfies an integrality condition. And so really what I'm doing here is I'm presenting the rank 1 case of the construction because I don't want to carry indices along, but I can later say how it immediately generalizes. Okay, now I think we decided not that we don't want too many computations. So let me let's do one computation. So let's write down a big commutator. Let's choose two complex numbers, alpha and beta, and look at what is the commutator of the argument in the exponent of E plus with the argument of the exponent in E minus. So, well, alpha and beta, they just go along for the right. And here we have a minus. And then I have the sum of all these commutators, but you see each commutator, let me maybe call this M, that we don't confuse ourselves. So for each commutator vanishes unless n is equal to m in that formula, and in which case I can replace the commutator just by an n. So that that means that this whole sum collapses to a 1 over n, right, on n over n squared, and then I'm sorry, I wanted to call this variable differently.
Sorry.
Yeah?
I think the first index should be from m minus 1 to minus infinity. So here you write from n.
No, they are going both from 1 to infinity. But the difference is here you have a negative, and here you have a positive.
Okay.
I could equally have written from negative 1 to negative infinity, but well,
Yes.
it's the same.
That means like minus infinity. Okay.
Oh no, this is not a minus. This is from the. But after the week you just complain, it would have been much better if we had removed the boards after each lecture and installed new ones, right? Okay. So we get this one, and this series is what is it? It's the Taylor expansion of the logarithm, right? Of the logarithm of 1 minus w over z. Okay, so now, now with this computation at hand, if we call this expression here, let me just call this give these two names. Blue was not a good idea. So then now these are the arguments in the exponent, and really what we want to understand is commutators of E plus with E minus. Yes?
That is acting on something, right? Like, I'm a little bit confused now because you take the commutator and you're saying that it just acts as a scalar on because we're thinking of this whole thing as an operator.
Yes. And it still acts as a scalar, yes. Right? It just because, it's a sum of commutators that's the same as the sum of the commutators. And because we are in the Heisenberg example, where any commutator is just a scalar, that happens. So you're confused, but this is just because we're dealing with a free field algebra here, and they are so particular simple. And that makes it also so particular nice to construct the delta operator now, because now let me recall if I have I know the commutator of two operators A and B. I have a formula for conjugating with the exponential, and it's just given by iterated commutators. And it goes on, right? So in particular, if the commutator of A and B is just a scalar, what you exactly pointed out, then of course the commutator of a scalar with anything vanishes, and then it truncates, right? So this means in our special case, we see from this, for our special case, we see, for example, that this our E plus and now I can equally well, of course, I can equally, of course, multiply this equation by e to the a from the right, so which I'm doing here in this formula. Then then I get this relation, or I can also formulate this as a commutator if I like. The commutator of this E plus with the argument of the exponential of E minus appearing in the E minus gives us just this logarithm times E plus back. So, and why did I do this experiment? So I'm presenting this because this is now quite nice to be very explicit with, right? So now I know the commutator of one of my exponential with the argument of the other one. So now I can use this formula again, interchange, and now replacing a and b, and this and this b becomes this E plus, right? And if I do this, I can now see what the conjugation with the E minus on E plus gives, and let's just write it down term for term. We get the constant term, then we have to do one commutator, which gives us the logarithm, but in the commutator, now here the commutator is not a scalar, but a E plus appears again. And so this means if I look at this this formula for the next subleading term, I have to take this answer and do the commutator again. This gives me a second power of the logarithm times an e plus. And now I can go on, right? And the next term here would be a 1 over 3 factorial commutator of a with this thing. So it will give me an additional power times e plus. And you see how it goes, right? It becomes, the e plus will appear as every coefficient, and then it is exactly the Taylor expansion of the exponential. So, and so that means we get and that we can, of course, evaluate to get one minus WZ e plus. And now we can multiply from the right with e minus, and we see, very nice, e minus and e plus have I mean, they don't commute, but they have this this nice formula. E minus times e plus is the same as e plus times e minus up to this 1 minus WZ over times to the minus alpha beta. Okay.
Sorry, quick question. In the calculation there, the E minus, should that have a W?
All right. Absolutely. I'm always holding my notes in the hand, but only half looking at them because you focus so much on the talking. And then, yeah, but it was only missing here. Yeah. Thank you. Okay. Right. So I would say in 1 minute. Yeah. But I think that it's better. Well, it is almost a good time. Yeah. So now, why do I do all this? Because now we define something called delta with maybe an index indicating what it depends on. And it is almost the e plus that I defined, that we also add an exponential of the zero mode of the Heisenberg algebra. So this is, and then the argument of e plus is not alpha x, but we also put some negative signs in there. And the lemma is that this satisfies the desired conditions. So that means A, B, C, D, exactly those conditions that in the previous lemmas guaranteed that you can twist a module. So let me just recall those. And then we have our break. So this means if I act on a vector, I just get a polynomial in Z and Z inverse. For any, yeah, exactly. Right, yeah, exactly. There will be the condition on alpha comes a little bit later. So yeah, the statement is exactly that this d delta alpha satisfies the desired conditions on V. And let's have a break. I can give a comment on the proof, and the proof is actually the duality is quite important. And but what we will then do is we will study how does this delta operator act on Fock modules, and then we can also think about your question again, but maybe won't discuss it in too big of a detail.